In section 6.1, we learned that the probability distribution of a discrete random variable can be shown to us in a variety of ways, most particularly a table, a graph, or a formula. In that section, we saw tables right here. They're lovely. And we saw graphs, which are essentially glorified tables, right? They're tables, but in graphic form. But now we also want to expand that idea to the formula idea, because tables and graphs are all well and good, but they have limitations. So first, let's look at some of those limitations by considering the NBA player example yet again. So remember that we had this average free throw percentage for an NBA player is 77%, which means the chances they will shoot a successful free throw. You are going to randomly select 3 random NBA players and have each of them shoot a free throw. So we created a tree diagram and did some calculations and figured out all these probabilities for each of these possible outcomes. So it could be each of them succeeds, success, 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 SSS. Or it could be the last one fails, so SSF. Or the middle one fails, so SFS, and so on. Now, these, first of all, I want us to kind of look at this table just a little bit. If you'll notice, I've color-coded it for you because some of these probabilities are repeating. So for example, all the ones that had 2 successes right here, the yellow ones, we could compile them together and make one probability out of it. And that's what I did down here. So if you see, each of those ones that are yellow, they have 2 successes. So what I could do is talk about them right here. 2 successes, 2 for the number of successful throws. And then where does the 0.4091 come from? That comes from adding up the probabilities for each of those 3 from the table above. So if you take 0.1364 plus 0.1364 plus 0.1364 and you add them up, you'll get about 0.4091. It's actually 0.4092 if you do it with your calculator like I did right here, 3 times 0.1364, but that's just because of a little bit of rounding error. So when I did this with my computer, I actually used more decimal places than I'm showing you right now. So here, I'll actually change it just so it matches what you guys would see. And then I'll change this right in here so you can have it be just the same. But it's an approximation anyway, because honestly, there are a lot more decimal places going on here, but I didn't keep them all. All right, so now this was a lot of time and trouble. Let me just remind you of the tree diagram for this. Let me back up several pages, 1 second. There, this was the tree diagram. It was the very, very beginning of the chapter. So we had to make this huge tree diagram, and then you had to figure out all these different probabilities, and it was really kind of a pain. And this was only 3 players. Terrible. And so that brings us back to here. We want something that will work no matter how many players we're talking about. What if it was 30 players? What if it was 300 players? There's 300 players in the NBA. What about that? What about 3,000 players that have played in the last 10 years or something like that? I want something that'll work no matter how big my number of players is. And what's more, what if it's not always 0.77? What if it's 0.72 this year and 0.81 this year and so on? I want something that'll work quickly and efficiently for all of these things. And that's what we're going to learn. Let me type that up 1 second. There we go. A formula would be a more quick and efficient way to find these probabilities. It would let us find them regardless of the size of sample or the probability of success. A formula as opposed to a table made from a tree diagram, or a table or a histogram, I should say. So either one of those would be terribly inefficient as opposed to a table or histogram made from a tree diagram. So we want something that'll work really quickly, and a formula will do that for us. And what's more, you're not actually going to use the formula yourself. You're just going to make the calculator do it. The calculator will know the formula for you, and you just have to know how to apply it. Now, before we can use this formula, which is called the binomial formula, very important stuff, we have to first realize when we can use this formula. This is going to be a powerful tool in your calculator, but you can only use it under certain circumstances. So let's figure out what those circumstances are. Number 1, you have to have an experiment that is performed a fixed number of times n. Each repetition of the experiment is called a trial. And I should say it's a random probability experiment, right? sort of goes without saying since this is a probability distribution, but let's say it anyway. So this is a random probability experiment. It's performed a fixed number of times. Each repetition of that experiment is called a trial. So for example, if you were going to toss a coin 4 times, then each toss of the coin would be a trial, and that gives you 4 total. But you're going to fix it ahead of time. You're not just going to keep tossing forever. Each of the trials is independent from each other. So every time you toss the coin, for example, if I got heads in the last toss, it has no bearing on whether I'm going to get heads on the next toss, right? They have to be independent. For each trial, there are 2 disjoint outcomes, success or failure. Success is usually abbreviated with a capital S, and failure is abbreviated with a capital F. And keep in mind, by the way, that success doesn't actually mean a good thing all the time. It's just what we determine what we're looking for. So if you're doing a study of schizophrenia and you determine success is schizophrenia, you don't really mean that that's a successful thing. You just mean that that's what you were looking for in your probability experiment. And the probability of success is the same for each of the trials. It cannot change from trial to trial. So again, with the coins, heads is success, F is failure, pretend. Then the probability of success is 0.5 every time. It doesn't change from toss to toss. If x is the number of successes in n trials, then 0 is less than or equal to x, which is less than or equal to n. So again with my coin. So if I imagine I'm tossing a coin 4 times, the number of heads, because I determined successes were heads, the number of heads I could get would be as low as 0 if I got tails, 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 tails. And the highest I could ever get is 4 because I'm tossing the coin 4 times by definition. Now, this whole idea of a binomial distribution is actually extremely important to us, and we are going to see a lot of it once we hit section 8.2 and beyond. So keep in mind that the concept you're learning here is very key to being able to work with polls and surveys in later chapters. But for right now, let's see if we can explain it for our particular problem. So we have the average free throw percentage for an NBA player is 77%. So that's the chances of a successful shot. You're going to randomly select 3 NBA players and have each of them shoot a free throw. Explain how this experiment is binomial and how the criteria are satisfied, and identify each of those variables. Actually, they're not variables, but they're constants for this particular problem. All right then. Well, remember what you need to have. You need to have a fixed number of trials, right? Fixed number of trials. Okay. Then you have to have independence. You have to have success and failure. That's 2 disjoint outcomes. And then you have to have the probability of success is consistent for each trial. All right, so let's figure it out. We have all 4 of them. Let's start with the first one. We have a fixed number of trials. Yes, we do, because we have 3 players going up to the line, right? The experiment is performed n equals 3 times. So there's your fixed number of trials. Are the trials independent of each other? Sure, they are, because each player's free throw success or failure has no bearing on the next player. I mean, if I'm Kobe Bryant and I go up to the free throw line and I make the shot, the next player behind me is not paying attention to what I did, right? Are there 2 disjoint outcomes? Well, absolutely there are. That's what basketball is built upon, right? You either make the shot or you do not make the shot. That's it. Those are the rules, right? So the ball either goes through the hoop and goes down the net, or it does not. So while we're on the subject, let's think about x. X is the number of successful free throws. Successful free throws. I should have done the layup shots or something, because it's easier to say. All right, so the number of successful free throws is possible. You could have 0, all 3 of them miss. You could have one of them succeeds. 2 of them, 2 different ones succeed, or 3, all 3 of them succeed. Those are your options for the number of successful free throws. Last but not least, is the probability of success the same for every trial? And if so, what is it? Well, if we define success as making the shot and failure as missing the shot, which I think is a pretty obvious one, then yes, it's the same every time, because the 0.77 is consistent for each player going up to the line, as it's the overall NBA average. Actually, when you play the game, usually every player has their own stats. So let's say Kobe Bryant, for example, let's say he's at 80%. And so he is set at 80%, and he will generally stay around 80% for most of his career. And honestly, professional players they're so used to shooting free throws that it becomes a more mechanical thing to them, and therefore it actually becomes less psychological, to the point where most professional players are actually independent of each other. So whether they make or miss the next shot is kind of irrelevant from their last shot, believe it or not. So all the people that kind of scream at them from behind the sidelines in general doesn't faze most players, because they make so many of those shots in their career. All right, so now let's see if we can apply this to some more examples. So we need to determine whether the following are binomial experiments, and if they are, we need to explain how they satisfy the criteria and identify n, x, p, and q. All right. Oops, I'm not sure why that had a space there. There we go. All right, so we have a loaded die that tosses fives 80% of the time. Cool. We toss that die 4 times and record the number of fives. Now you might think, oh, that's not binomial because it's a loaded die. Oh, but it is binomial. So let me type this up 1 second. All right, so was this performed a fixed number of times? Yes. The experiment was performed n equals 4 times set in stone. Were the trials independent? Absolutely. The die has no memory of its last toss. I've played games with people that are convinced that their die is jinxing them and they'd switch to another die, and I always say that die doesn't remember what you rolled. It doesn't. It's independent. Are there 2 disjoint outcomes? Yes. You either roll a 5 or do not roll a 5. Notice rolling a 5 isn't necessarily a good thing, but success doesn't mean that. Success means what you were looking for, which is 5s. The number of possible 5s you could have tossed in 4 tosses is your x value. So that's going to range from 0 all the way up to 4. And the probability of success is the same for every trial. Yes, it is. It's 0.80 because that was what the die was loaded for. And that means the probability of failure is 0.20. There we go. All right, now what about that same loaded die that tosses 5s 80% of the time? You toss the die and record the number of rolls it takes to obtain a 3. Well, that's not binomial because you could toss 2 times, 3 times, 4 times. It's not binomial because your number of trials is not fixed. Right? So number of trials not fixed, that is no good for you. I'm just going to put dot, dot, dot at the end of this. It could be 2, 3, 4, 5. You could toss it 10 times to get a 3. What about the Agency for Healthcare Research and Quality reported that 53% of people who had coronary bypass surgery in 2008 were over the age of 65. 15 random coronary bypass patients are sampled, and the number who are over 65 is recorded. That is binomial. All right, let me write that up 1 second. All right, were there a fixed number of trials? Yes, you're looking at 15 patients. Capitalize the E there. All right, so were the trials independent? Sure. Because the patients are random, their ages will have no bearing on each other, right? They're random patients, so whether one of them's over 65 doesn't really affect the other one. Are there 2 disjoint outcomes? Absolutely. Either the patient is over 65, that's defined as our success because that's what we're looking for, that's what we're recording. And then failure would be the patient is 65 years old or less, right? Over 65 means they can't be 65. So they gotta be 66 and so on. And then X would be the number of coronary patients over 65 out of 15. So that goes everywhere from 0 to 1 all the way up to 15. And the probability of success is 0.53. So the chances of the patient being over 65 is 0.53. So the chances of being 65 or less is 0.47. And that's consistent for, not for the toss, sorry, it's consistent for each patient, as that's the overall average from the study. Okay. All right, last but not least, a jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. Everybody see that? That's a problem. The random variable represents the number of red marbles chosen. And this is definitely not binomial because without replacement, you're affecting the probability of what's left. And that means that the trials are not independent and your probability of success keeps changing as you go along. And I made a note of that right here. In general, experiments done without replacement are not binomial because of what was written above. All right, we're all done with that section. I'll see you back here to actually start applying the formula next time.